So now we get into Young's double-slit experiment. So at this point, we've had about 200 or so, well, maybe 300 years of uncertainty on the nature of light. So is light a wave or is it a particle? We have some in the particle camp, some in the wave camp, but more believe it's a particle than a wave, based on the fact that it was Isaac Newton who proposed that theory. Thomas Young was a famous physicist who ends up examining this more in depth. And this is section 9.5 from your text. So it says here, at the end of the 1600s and into the 1700s, the debate over the nature of light was in full swing. Newton's theory of light particles faced challenges from leading scientists such as Christian Huygens. Huygens' writings on the wave theory of light proposed that light traveled in waves through an omnipresent ether, like sound traveling through air. So Huygens ends up coming up with a solution for his light traveling through a vacuum problem. And his solution is he theorizes something called an ether. That space isn't exactly a vacuum, but it's actually as if there's a medium outside in space. It's called ether that everything is sort of swimming in. So it's almost like space is this large ocean, for example. And his idea is that it's the ether that is allowing the light waves to propagate. So during this time, many researchers focused on the question of interference. They said if light behaves like a wave, a similar experiment using two light sources should reveal bright areas of constructive interference and dark areas of destructive interference. So we see in the bottom there a picture of water waves interfering. And this will help explain to you why we were studying water waves earlier when this unit's about light. And it's that if we see interference in water waves, which are large enough for us to see and easily replicate in experiments, we should see the same for all types of waves. And we do for many waves, but for light it has not been observed up to this point. And there was a lot of attempts to do so, but not a lot of success. So we know why these experiments failed. And this kind of goes back, I think 2 lectures back when we were talking about interference of water waves. We knew that the waves had to be coherent in order for us to notice an interference pattern. So coherent waves means that they have the same phase or a fixed phase difference and frequency. And in terms of light, light can be many different frequencies. So we see light in a range of different colors, and when we get into the electromagnetic spectrum a bit later, we'll see how many nanometers in terms of wavelength does the light have to be in order for it to produce that type of color. The light that we see could be in any random wavelength that is within the range of a light wave. So without being able to fix that, we can't have a coherent wave. Also, in order to see the interference, these waves have to be of the same frequency, or rather wavelength and frequency kind of answers that, but they have to be of the same phase. And just because a light's originating from a singular point, it could be many different light waves that are originating from that point. And they could be at various locations in their phase. So we need a way to set the phase of the lights to be the same, or of a fixed distance apart. And we need the light to be of the same frequency or wavelength. The other issue is that the distance between the 2 light sources has to be of the same order of magnitude as the wavelength of light. So when we're talking about in order to observe an interference pattern, the distance, or the distance of the 2 slits the light would have to appear between, or the distance of the two sources, rather, not talking about slits yet, the distance of the two sources needs to be on the same order as the wavelength. And light is a very, very small wavelength. So that distance would have to be very small as well. So while experimental conditions were difficult for scientists to recreate in the 1700s for this type of experiments, it was coherency that was the most difficult. So physicists could produce light of one frequency, but before the inventions of lasers, coherent light sources simply did not exist. In addition, since physicists did not even know whether light behaved like a particle or a wave, they had no way of knowing what wavelength light might be. So it took nearly 100 years after Newton and Huygens presented their theories of light for the debate to be resolved. So it was actually 100 years. Sorry, I was a bit confused on when Thomas Young started this experiment. So it was at the end of the 1700s that Thomas Young devised this experiment that can basically give us coherent light. So he wanted to see an interference pattern with light. So what he does is he uses one monochromatic light source. Young allows the light to fall onto an opaque material with a single narrow slit. So we have S as our light source, and then we have a slit. So basically the light's hitting a wall with a little hole in it. So if we saw this with a water wave, we know that if that slit was small enough, we'd start to see kind of an interference around it. Not interference, but a diffraction around it. But we wouldn't see, but what we would not see is an interference pattern because we can't have two light sources. So what happens next is he creates he introduces a double slit after the single slit. So what's happening here is the source of the light, which is of many different wavelengths, hits this slit, and it diffracts from that slit. Its point of diffraction now at the single slit is now a new source of light. But at this source of light, at this point, we only have light of one wavelength. And if we introduce that to another slit, these light sources, or the two new light sources we create at the double slit, are now coherent. They have the same frequency, and their phase distance or difference is comparable to the distance between the two sources, which is the length of that double slit. So this gives us a way to test the interference pattern of light for the first time. And I'll read here. It says, the light that passed through the double slit barrier fell on a nearby screen, producing the historic pattern of light and dark lines caused by the interference of light waves. Young's result catapulted the wave model of light into the center stage, where it would remain unchallenged for more than 100 years. So we have the monochromatic light source that hits a single slit. That creates a single light source of one phase. It hits the double slit. We now have two light sources of the same frequency, but out of phase by that slit distance. And it creates a pattern of light and dark fringes. And I'll show you what that looks like on the next slide. So it says, Young experimented with this setup for more than 2 years before he realized that the double slits had to be so close together that they almost appeared to be one slit to the unaided eye, meaning that that wavelength of light must have been very, very small. So he had to make this slit very, very, very small in order for this to happen. And we're talking nanometers. So what happens, or rather hundreds of nanometers. So what happens now is, this is the pattern we see. We see in the center, we see the very bright area of constructive interference. And then we see our first nodal lines, where we have those two lines of darkness. And then we have the next bright fringe, and then the dark fringe, and then bright fringe and dark fringe, and so on and so forth. So this experiment now convinces people that maybe Newton wasn't correct, and that maybe Huygens was correct after all, and that light is a wave. So this happens in the late 1700s, early 1800s. So light, the understanding of light goes from we're not sure if it's a wave or a particle. Newton says it's a particle, so we're going to say it's a particle, to, well, Thomas Young kind of proved Huygens and proved Newton incorrect, so we're going to say it's a wave. But then there's still this idea that, well, how do we travel through the vacuum of space? And this idea of an ether comes up. But let's go back to Thomas Young. It says Thomas Young was successful where others had failed for several reasons, and I'd like you to copy this down. It says he used a monochromatic light source, so a single wavelength light source. The double slits acted as two sources and were spaced much more closely together than possible if two separate light sources were used. So it wasn't possible to put two light sources next to each other that close. The light passing through the initial slit acted as a point source. When a wave front from the point source reached the double slits, two parts of the same wave front became new sources for the double slits and were therefore coherent. And this slide here also summarizes that, but in a little bit less detail. It says, early attempts to show the interference of light were unsuccessful because the sources were not coherent and the sources were too far apart. And I'd like you to copy down that image you see there of Thomas Young's double-slit experiment and be able to explain that. Also, you can copy this down so that you have more notes on that experiment. And further, copy down here where it says what we ended up seeing, and you see at the bottom of that image there, is this famous interference pattern of light, where we had light and dark fringes, and they resembled the same types of interference pattern we would see with water waves in a ripple tank. And this was our main evidence that light is a wave. So now we're going to look at this experiment, and we're going to try to analyze it a little bit more mathematically. So the bright and dark fringes are alternate regions of constructive and destructive interference. So to analyze the interference, you need to determine the path length difference between each slit and the screen. And we're dealing with very large orders here. So the distance to the screen is very large compared to the distance between the slits. So that makes our math, there are ways to simplify our math a bit. You can see on the side, on the right at the top, we see the bright fringe, the central bright fringe occurring, where we have our constructive interference of the two sources, S1 and S2. We have the dark fringe occurring at the a point where the source from S1 and the source from S2 kind of counter each other out. And another bright fringe occurs in the lower image when we have, again, constructive interference. So here's some things we do to simplify the mathematical analysis of this. So since the screen is a long way from the slits, we can consider that L is going to be much, much larger than D. Because that D, that distance between the slits, is going to be very, very small, but the distance to the screen is going to be of the order of about a meter or so. So since L is very, very large compared to D, the path lengths L1 and L2, so look at the two images at the bottom now, A and B, that are labeled. So if this goes back to the equation we had that we used a lot on that worksheet, where it was P1S1 minus P1, PNS1 minus PNS2. That distance, right, that difference between those points, right, we can now consider that the L1 and the L2 are essentially the same distance. They're going to be different by a very small margin. So we can just treat it as an L instead of considering L1 and L2. And we can also consider that, this is another thing that's a bit odd, we can consider that those lines are actually parallel to each other because they're traveling, in image A, it obviously looks like a triangle. L1, L2, and D make a triangle. But if we zoom up on the left side of that, where D is, it would appear as if L1 and L2 are parallel lines. So we can treat them as parallel lines for that analysis on the that close-up analysis on the slit distance D. We also know that because the wavelength is much smaller than D, we can also simplify this a bit further. So this gets us to, using the equations we had previously, we can now simplify this into delta L is equal to D sine theta. And constructive interference, so looking at our other equation that we were using before, constructive interference occurs when, and we're going to introduce an M for maxima because that's when the constructive interference occurs, and an N for minima where the destructive interference occurs. So it's D times sine of, D times sine of theta M, where M is the maximum number, equals M times lambda, where M can be 0 if it's the main one, the first one that occurs, or the 0th order, and then the first order maximum, second order maximums, and so on. Then if we look at the destructive interference, it's the same idea, but now it's offset by n minus 1/2. So these equations look very similar to what you were using on that worksheet. They are the, you can copy them down here. These are the Thomas-Young's double-slit experiment equations. So we have sine equals theta m equals m lambda over d, or sine theta n equals n minus 1/2 lambda over d. So m is the maxima. These occur at the bright fringes. And the first one that we have, the one in the middle, is the 0th order, or the 0 order bright fringe. And then we have dark fringes that occur. Those are the first order dark fringes, then the first order bright fringes, second order dark fringes, second order bright fringes, and so on. So we'll look at how to calculate this. This question says the third order dark fringe of 660 nanometers of light is observed at an angle of 20 degrees when the light falls on two narrow slits, and we're asked to determine the slit separation. Okay, so the first thing we do is we have to determine if we're using the destructive interference equation or the constructive interference equation. And some of the words you're looking for are if it says at a location of destructive or constructive interference. Other things you can look for is if it says it's a dark fringe, then that's destructive. If it says it's a bright fringe, that's constructive. So because it says this is a third order dark fringe, I'm going to write down this equation here, n minus 1/2 lambda equals d sine theta n. Oops, sorry, right there. Now this tells us our n is going to be the order. So it's a third order. So I'll write down here 3 minus 1/2. Our lambda is our wavelength. And in this case, it was 660 nanometers. So one way I like to write nanometers, it's always times 10 to the negative 19, or negative 9. So 660 times 10 to the negative 9. When it comes to D, that's what we need to solve. And I should have rearranged this first, but that's okay. And then when it comes to sine, we're going to use sine of 20 degrees. Now, I have to solve for D, so that's going to be this 3.5 times this divided by this. So putting this all in the calculator at once, 3 minus 1/2 is going to be 2.5 times 660 times 10 to the power of negative 19, or sorry, 10 to the power of negative 9, divided by sine of 20. And that gets us to 4.8 times 10 to the negative 6. And looking back at the question, we had 660 and 20 degrees. So the degrees isn't as important, but 660, we can only assume two significant digits for that. So our value has to have two significant digits, 4.8 times 10 to the negative 6 meters. Next, well, let's go back here, because I think we don't actually have a question next. We're going to do a little bit more of the lecture. So another equation we can come up with here. It says, in addition, the equation to determine the distance of each bright fringe from the center of the screen, m equals 0, is xm equals ml lambda over d. So this is the distance from the bright fringe to the next bright fringe. So this value we use to end up calculating the distances between the fringes. And we can also do the same for the distance between the dark fringes. And it's basically the same idea, n minus 1/2 for n, and times the length times the wavelength divided by the distance between the slits. So it says, although L actually has different values for each maxima and minima, L is so large compared to D, and the values of L for the various nodal and antinodal lines are so similar that we treat L as a constant, being essentially equal to the perpendicular distance from the slits to the screen. So that L is actually different at each time, at each angle, but because it's such a small difference, it's not going to affect our results. So I'd like you to copy this down. This xm and the xn is the distance between the maxima and the minima from the center of the screen. And there is no x when m is 0, because the answer would be 0 in that case. Well, I guess there would be. If you substitute 0 in for that equation, you'd end up with 0. Okay, let's try this question. It says two slits are separated by 0.2 millimeters, and they produce an interference pattern. The fifth maximum is 12.8 centimeters from the central maximum. The wavelength of the light used is 550 nanometers. We're asked to determine the distance at which the screen is placed. So for this question, let's put our calculator on too, because we'll need it eventually. We have two slits, right? We have to figure if it's constructive or destructive interference, and because we're talking about maximum, we know that it's constructive. So we're going to write this equation down. Lambda equals d, and I know in your book or your formula sheet it's similar to. We'll just put equals just to make it easier. And what we need to solve for is the L. So rearranging this equation, I have L equals d delta x over lambda. And this becomes, d is millimeters, so 0.2 times 10 to the negative 3. The delta x is in centimeters, so 12.8 times 10 to the negative 2. Divide this by our 550 times 10 to the negative 9. So let's put this in our calculator here. Oh, actually, we can't put this in the calculator yet because we're missing something very important. I wrote down the wrong equation. This is supposed to be the maximum equation, so I wrote down the one below it. So this m has to be here. And this m is the fifth order maximum, so I got to put a 5 in there. So when I put this into the calculator, it's 0.2 times 10 to the power of negative 3 times 12.8 times 10 to the power of negative 2 divided by 5 divided by 550 divided by 10 to the power of negative 9. And that gets us to 9.3. So L is 9.3 meters. Okay, next. So in either case, the separation between any two adjacent fringes is delta x equals L lambda over D, which can then be rearranged to determine the approximate wavelength of the light, which is lambda equals D delta x over L. So this was what I was trying to do earlier. This is the Young's double-slit experiment and how he ended up determining the wavelength of light. Oops. So on this slide, you can copy this down, and this is lambda equals D delta x over L. This applies equally to the dark or the bright fringes, and it's only good if we have very small angles. So let's try another problem here. It says a double slit experiment is carried out with slit spacing D equals 0.41 millimeters. The distance to the screen is 1.5 meters. And the bright fringes at the center of the screen are separated by a distance of 1.5 millimeters. So, using this information, we need to find the wavelength of the light. And to do this, we know that lambda, do it over here, equals D, or is close to equaling D delta x over L. So lambda equals D, which is 0.41 times 10 to the negative 3. Delta x is 1.5 times 10 to the negative 3. And the L is 1.5. So putting this into our equation, we end up with 0.41 times 10 to the negative 3. I'll just do it the way it's written. Times 1.5 times 10 to the negative 3 divided by 1.5 meters. And if I have this value here and I want to write this in nanometers, I know it's not written in nanometers where you have it, but if you ever want to write something in nanometers, you multiply it by 10 to the power of 9. So it's 410 nanometers. And I usually prefer that things are written that way when we're talking about light because it's easier to understand. And you'll understand that when we get to the electromagnetic spectrum. But I think the limitations of the course website might not allow you to write 410 nanometers. So we'll see how that works. Next part of this question says determine, oops, I don't think you see it there, so I'm going to turn this off. It says determine the spacing of the bright fringes when we use a 600 nanometer source instead. So using that same equation now, we'll do it on this side. Lambda equals D delta x over L, and we're solving for delta x, so that's L lambda over D. Our L is 1.5. Our lambda, we were told to use 600 nanometers. And our D is 0.41 times 10 to the negative 3. So what is our delta x going to be? What's the spacing between the slits going to be? 1.5 times 600, that's 300, times 10 to the power of negative 9, divided by 0.41, divided by 10 to the power of negative 3. And we end up with 2.2 millimeters in this case. Or 2.2 times 10 to the negative 3. Okay, now going back here, we have another question. It says, in an interference experiment, red light, 600 nanometers, passes through a double slit on a screen 1.5 meters away, and the distance between the first and the 11th bands is 13.2 centimeters. So we're asked to find out what is that delta x, that spacing. And it's kind of shown for you here already, so I won't write it down. But when you're given something like this, from 11 to 1, that's 10 different spacings. Because it's from you're starting at 1, then when you go to 2, that's you count 1 spacing, 3 is another spacing, and so on until we get to 10. So we just divide that by 10. So now we know our delta x. And I won't actually work this one out. It's pretty simple after that. Once we know our delta x, we put it into the equation. We can find out what our d is. It says, what would the spacing be between the adjacent nodal lines if you use blue light instead? And I'll let you use this one, do this one as well. You can just substitute that in. It's not too difficult at this point. So now there's a few other things to talk about with the wave theory of light that we end up coming up with after Young's experiment. So Young's evidence for the wave nature of light was not accepted by the scientific community until 1818, when Augustin Fresnel proposed his own wave theory, complete with the mathematics. Simon Poisson showed how Fresnel's equations predicted a unique pattern when light is projected past a small solid object. So this, if we have a disk and we have a point source, we will be able to see a bright spot. If the light is interfering as a wave, there will be a bright spot behind the object. So Poisson's argument was that if light behaved as a wave, then the light refracting around the edges of a disk should interfere constructively, produce a bright spot at the center of the diffraction pattern. This could not happen with the particle theory of light. And this was kind of what put the nail in the coffin for the particle theory of light, or the particle theory of light for quite some time. So in 1818, Poisson's prediction was tested experimentally by Dominique Arago, and to many people's surprise, he successfully observed the bright spot, which we now call Poisson's bright spot. The experiment also verified the wave theory of light. And you can see in that experiment there, we have very bright light around the edges of this disk. This is just the pattern on the wall, but there's a bright spot in the middle. And Poisson, of course, was a theoretical physicist, so he didn't do the experiment. It was Dominique Arago who did the experiment, who tested his theory. And that's something we'll see in physics. There are theoretical physicists and experimental physicists. The theoretical physicists devise the thought experiments that something will work, and the experimental physicists design the physical experiments to make sure that the theory is correct. So you can copy this down for the wave theory of light and Poisson's bright spot. And we'll read through this last slide here. It says, by 1850, the validity of the wave theory of light had been generally accepted for some time afterward. Generally accepted. So for some time afterward, the mathematical consequences of the wave theory were applied to numerous aspects of the properties of light. But there is the big problem, right? The wave theory of light was not adequate to explain the movement of light through the vacuum of space, since waves required a material medium for their transmission. So this was that ether idea, this fluid of space. And they did a number of experiments to try to find this ether, but none were successful. So I guess we'll stop with this last question. It says, so is light a wave or a particle? What we actually find out later is that it's both. There's a wave-particle duality of light. And you can read what it says here, but we'll get into it a little bit more in one of our some of our next lectures as well.